a minute to write it up and then this is just a summary of what you need to know, okay? I'll be in my office around 1 p.m. on Monday. You can come by and pick up your either the sheet or the graded exam. I hope to have your exam graded by Monday. If not the exam, at least the sheet from your first exam you can have it by Monday afternoon. I have a mock exam printed out. I've written unlimited sheets of handwritten notes. And I have to do this because some of you complained you don't have a paper copy of the book. If I say open book, I'm disadvantaging those individuals. I'm ready to do open book. No. No. I don't know when they gave the chance or the option for you to schedule the exam. Okay? Yeah.
And not print any 3 notes, right?
No printed, only handwritten notes. You can bring as many sheets as you want. Okay. Whatever integrals you'll need, I'll put it in the exam. I mean, you should know basic integration. You can't ask me what is integral cos x. If you that I won't provide. Some complicated integral or identity I will provide. Okay, so I'm going to erase this side. Hopefully people have written up this. Yes, anyone writing? Anyone still writing this? No? So up to here is sort of a review of chapter 5 or module 2. From now I want to jump to the actual chapter on PDEs. I also printed out the mock exam, like 10 copies. Since you all sit together, maybe you can share. Can you pass to them? You can share. I'll come back if I have enough. Do you have one? I have one. Can you both share? Who doesn't have one? So this is the format I intend to follow. First equation or first problem will be a problem on Laplace equation in rectangular domain. Before that, let me start the summary of uh, chapter 12 and then we'll discuss this mock. Okay. So in chapter 12 is PDEs and it is the module 4 according to our syllabus. What did we do? Section 12.3 wave equation and heat equation in 1D, that is 1D Cartesian. So UTT equal to C squared UXX, UT equal to C squared UXX. We saw this. Mainly what you want, what we started seeing there is the idea of separation of variables. To say U of x comma t is f of x times g of t. This is the starting point for all our solution processes. Okay. So by providing the section number, I'm hoping I'm hinting to you which problem or which problem sets to try at home. Okay. And then section 12.6 Laplace equation in 2D Cartesian coordinates, which is uxx plus uyy equal to 0. We saw this. This will result in the single Fourier series. That is Fourier series with only one index changing. And then we also saw the section 12.8 wave equation in 2D Cartesian. So that is UTT equals C squared UXX plus UYY. This will result in a double Fourier series. And for the time domain, you will have a trigonometric solution. Trigonometric solution for time. We never saw the heat equation in 2D, but considering that we have seen very similar equations, I would think that you should be able to handle this if it is presented to you. So this is all related to Cartesian we saw, and I'm telling you right now in the exam, a problem related to Laplace equation in 2D is going to appear. And I hope some of this will be useful when you do your project, second project. This is problem 1. So before I move further, let me talk a little bit about what we want to accomplish with the Laplace equation. So the domain is a rectangular region in general. This is length A. This is height B. A comma 0. Zero comma B. So in the discussion we did on this topic, the boundary conditions we saw were, if I remember correctly, what we did in class was to say u equal to 0 on 3 phases. Phase 1, 2, 3, and then on 1, 2, and 3. And u is equal to f of x on 4. This is what we did while we did the problem. Okay. What you could expect in the exam is either a combination of, in the exam, a combination of u equal to 0 and ux or uy equal to 0 on the different phases, and a suitable function for f of x on one of the phases. The method separating variables is sort of a, it works well if you reduce your boundary conditions to simple numbers and then proceed. So in the exam, I don't want to give you too many arbitrary conditions. Like I can't put u1, u2, u3 on all sides and ask you to solve. That theoretically is possible, but practically will be very tedious. So if you see problem 1 on the mock, the boundary condition we are doing here is u equal to 0 for x equal to 0 comma y, which is phase 3. On phase 3, u equal to 0. On phase 2 as well, x equal to a, y is a variable. And then uy is 0. Uy is 0. That is, in this phase, we are saying partial u over partial y is 0. Uy is 0 on phase 1, and u equal to a function x times a minus x on the fourth phase or fourth side. So if you look at this, this boundary condition, on this face and on this face, u is 0. You can go through the process, but what you will find out is that u will be sine n pi x over a. Because when you separate the variables, you are going to get f of x, f of 0 and f of a. One of them will imply the arbitrary constant multiplied with the sine is means by the cos is 0, and the other will imply n pi by a. That is, if you write d squared f over dx squared plus k f equal to 0 or k squared f equal to 0. So we have f of x equal to a cos kx plus b sin kx. F of 0 equal to 0 implies a is 0, and f dash of a equal to 0 implies a equal to n pi over a. The spirit of the exam is for you to have enough intuition about this procedure so that you could quickly get two ODEs and look at them and quickly move from here to here. So if you know this equation and you look at this and you're going to know that it's a trigonometric solution, with the boundary conditions, you quickly reduce the problem so that you get Fn of x equals, let's say we will call it Bn sine n pi x over a. The other boundary condition has u of y or partial u over partial y to be 0. Okay, so what is the other equation? You have d squared, let's call it g, d squared g over dy squared minus n pi over a squared times g equal to 0. So g of y equal to, I call this C1 exponent of n pi y over a plus C2 exponent of minus n pi y over a. Now you would want to use this boundary condition. Use g dash of y equal to 0 to get a relation between C1 and C2. Which will essentially mean C2 equal to C1, and this function will simplify as Gn of y is, let's call it C times cosine h n pi y over a. Do you all feel you can take it home from here? Like the next step, does it look obvious to you? Yes?
The G function is for which space?
The g function is for this fix. I mean, you are obviously going to start by writing u of x comma y is f of x times g of y. I assume that, or I implied that. So now you have figured out, or you have reduced the problem to just one arbitrary constant. You can multiply Bn and Cn and call it some new name. It is just one more constant to evaluate, which you can evaluate using the information given about the fourth side. So you would write B and C, we'll call it D. So that dn sine n pi x over a cos h n pi y over a summation from 0 to infinity is equal to u of x comma y. The fourth phase is y equal to b, right? So we'll write summation n equal to 0 to infinity dn sine n pi x over a cos h n pi b over a equal to u of x comma b, which is given as x times a minus x. So then evaluate dn's. So to do this integration, you would need to know what is integral of sine n pi x over a multiplied by x times a minus x dx, which is like asking you to know what is integral of x sine n pi x over a dx. So if I'm going to provide information, I'll be giving this formula x power n, or let's give it a different title like x power k sine omega x dx. And to give you more information than necessary, I might also give you x power k cos omega x dx. And you should pick what you need to use to get the dn's. Okay. So this problem ends here with the determination of dn's through integration. Actually, this was not 12.8, 12.9. Okay, you are okay with this? Any questions, comments?
So I guess I'm just making sure I got the process right in my head, where basically you're just going side by side, or like, I should say like base by base, using whatever boundary conditions you can
Yeah.
to get. Okay.
In what sequence you would do that is like the art or your experience or practice. If you immediately look at this and recognize u is 0 on this face and this face, which is possible with a sinusoidal function. So when you reduce it, you will get this f of 0 and f of, sorry. No, this is f of a. I don't know why I put the dash. F of a. So yeah, this if you do a few problems, it's easy to catch the pattern. Okay. So moving on. Section 12.10. We saw the Laplace equation in polar coordinates, in polar or cylindrical polar which would be URR plus 1 over R UR plus 1 over R squared U theta theta equal to 0. This is what will result in a Fourier Bessel series. So this is the one I posted as a handout. Okay, so if you go back to PD1 handout, this is the domain in this case. First of all, the surface of interest is a circle. So here is the origin, and let's say this is uppercase R. And you could specify U on the surface of the circle. We will call this U of R comma theta equal to F of theta. This is one boundary surface. That is, the circle is a boundary surface, and depending on which direction you are looking, if you are interested in if R, the radius less than R less than infinity, then you are interested in the exterior domain. So your solution should be R power minus n. If you are looking inwards, 0 less than R less than radius, then your domain is interior, in which case it scales with R power n. Either case, the first few steps are similar. You will start with the statement of separation of variables, saying U of R comma theta is, what is the notation they use? W. W, and I will just use our own notation. We'll say F of R and G of theta. For F of R, you are going to get a Bessel's equation. Bessel's equation for F of R. F of R. And a second order ODE of the form G double prime plus some K squared times G for G of R. That's what you will get. G of theta. G of theta. G of theta. So this could be like a two-dimensional ideal flow or inviscid flow or an electrostatics or an elasticity problem, where if you are interested in everything from R to infinity, the boundary condition you would use, that is for exterior domain, the second boundary condition you would use is limit R goes to infinity, U of R comma theta should go to 0. For the interior domain, partial U of partial R at R equal to 0 should be 0, or you can also say U of 0 comma theta should be analytic, which is your reason to reject the second Bessel's function, or Bessel's function of second kind. Okay, actually, wait, it's not Bessel's equation. You are going to get a Euler-Cauchy equation. Euler-Cauchy equation. So the solutions will be of the form R power n and R power minus n. Either this or that. So for further details, I would encourage you to study this PD1 handout that I posted. and try a few problems. So the problems to try related to this would be problem 4 to 18, problem 4 to 18 from this problem set. So try different values of this f of theta as a boundary condition, and you can solve for the Fourier coefficient. Yes.
For the exterior type, shouldn't be the limit should be limited? I mean, it shouldn't go to infinity, right?
I said exterior.
Yeah, for the exterior part, why do we say the limit should be 0? Shouldn't,
It can go to any constant which you can subtract out as a baseline and redefine the variable and still make it 0. So the arbitrary, it's like saying what is the energy value at infinity? It can be anything you subtract.
Oh.
So the two types of domains you can imagine, interior and exterior. The third type would be annular. Where did I write this? So I'll write it here. Annular domain, which is like saying here is origin r equal to a and r equal to b. So you could have a boundary condition, say u1 or u of r a comma theta and u of b comma theta. And if you see your mock exam, I think the numbering is a little bit off. You want to rename this 1, 2, and 3. Okay. So in the mock exam, problem 3 is a Laplace equation, but not in cylindrical polar, but in spherical polar coordinates. But what I would tell you is, problem 3 is going to be a Laplace equation in either cylindrical polar or spherical polar. One or the other, not both. Problem 3 will be a Laplace equation in cylindrical or spherical polar, one or the other, not both. But the principles remain almost the same, except you will get a different equation for the f of r and for the ODE, which we'll come to, okay? So I'll start summarizing it here. Problem 1 is a Laplace in 2D. Problem 2 is a Laplace in either cylindrical polar or spherical polar. Okay, once I finish my summary, maybe we can try at least one example on P2. Okay, maybe we can do the problem that's given there. As I've written this is like P3, but you can assume there will be 3 problems, one of which will be a Laplace in cylindrical or spherical. Yeah. We are going to discuss it. Yeah, I think the first problem we went almost to the last step, so we'll discuss the remaining. Okay, I still want to make one more point and come back to this. So this is in cylindrical polar, section 12.10, spherical polar, section 12.11. Here you have r and theta, here you have r and phi. Okay. What I won't ask, I'll tell you, I won't ask r and z. in cylindrical polar. Not going to ask that. Okay. I'll also not ask r, theta, and phi in spherical polar. We are not going to do that. We are also not going to ask r and theta in spherical polar. So you can keep it clearer. Okay. So this equation, spherical polar equation, is of the form 1 over r squared, partial derivative with respect to r squared partial derivative with respect to r, plus one over sine phi times or sine squared phi times so the domain in this case is a sphere. I don't have a good way of drawing a sphere because my drawing skills aren't my strength. So this surface is defined as r equal to r. Okay, and we specify the boundary conditions u of r comma phi equal to f of p. So we specify a temperature or a voltage or anything, any scalar quantity on the surface, and same logic applies for interior and exterior. So if you assume that u of r comma phi is f of r comma times g of phi, you will get again an Euler-Cauchy equation for f of r with roots r power n and r power make sure I get that right. Yep. R power minus n minus 1. That is the form of the solution. And for g of theta, we'll end up with a Legendre's equation. G of theta. Okay, we'll try to do one example. Okay. So to work on this, I would suggest problems 12 to 20. Problems 12 to 20 in this problem set. Just the first. Let me make sure. No, actually, it's the whole equation. So I should write r squared. Thank you. So we did Cartesian, cylindrical, or spherical. That's going to be one of the problems. And the so if you see also in section 12.10, you have the wave equation in cylindrical, or more to say radial form. That is, we wrote second derivative with respect to time equal to c squared urr plus 1 over r ur. Yep. We did this derivation. So what you're going to get is for the time domain, trigonometric functions. And for the radial direction, you'll get Bessel's function. And since we promised ourselves that we are not going to invoke the Bessel's function of second kind for either interior or exterior domain, your function, let's say you call it h of r equal to C1 j nu of r plus C2 y nu of r, we'll just assume C2 will be 0. Because you have to keep that solution finite and analytic, we'll just deal with only the Bessel's function like we did in class.
Or wave equation, is that, plus whatever or dr in the way?
Yeah. So the domain for this looks like this. Can be r equal to a to r equal to b if a equal to 0 and b equal to r, that is an interior domain. If a equal to r and b equal to infinity, that is an exterior domain. And if a not 0 and b is greater than a, that will be an annular domain. I won't ask annular domain because we don't want to deal with this second kind in the exam. Okay, so it's going to be either this or this, not this. So this is your third problem. I confused the nomenclature. Anyway, it's one of the three problems. The three will be related to this wave equation in either cylindrical radial form or spherical radial form. We didn't see this in class. It's just the first term 1 over r squared, partial derivative r squared u of r. Everything else, now the domain becomes a sphere instead of a circle. Okay.
Yeah, nu be determined for h of r.
Come again?
How will nu be determined for h of r?
We'll choose it. We'll choose it to be minus n times n plus. Or sorry, we'll choose it to be minus n squared. All right. So I'll write here P3 P3 is wave equation in cylindrical or spherical radial form. Wow, that's a lot of combinations, right? Still, it can be very difficult to cover all this during your preparation between now and Monday. So what I'm going to do is to also tell you that we'll do Laplace equation in spherical and wave equation in cylindrical, or sorry, wave equation in cylindrical radial. So this is what you need to really practice for the exam. after all the different combinations and everything. Yeah.
Will the problem three have a chance to be a heat diffusion instead of a wave, or is it frustration?
We'll just keep it wave equation. We could make it heat, but if you see that it can be made, which means you will figure it out when the situation comes up to you. So you're okay. Yeah.
Exam is more about. We see what we're doing. We have the forms of both, what's it called? The forms of our equations after our separation of variables. You
Yeah.
care about us finding the C1 and C2 values or whatever the arbitrary constants are.
Yeah.
Not as much deriving the fact that we get Euler-Cauchy and Lenardon for that.
Thank you for the question. I would prefer it if you don't spend time deriving this. If you can, I'll write the 4 steps that I'm really wanting you to master. Okay. Step 1, you want to write or you want to start with the separation of variables, the idea of separation of variables, and state variables. And you want to state your function u, which could be x and y, or r and theta, or r and phi, and write it as a product of 2 functions, say like x of theta, h of x, g of y, f of r, g of theta, h of r, w of theta, or something. So you want to first make sure you tell me that you have understood the core concept that we have been going on and on for like 4 or 5 weeks. And then you want to obtain the 2 ODEs. This is a key step. If you are supposed to get credit for the first step, that is only if you show me the 2 ODEs correctly. If you make a mistake there, that's you already have lost some points. Step 2, use one of the ODEs and suitable boundary conditions to obtain a general solution. Not the entire solution, but the general solution for H or G or F or whatever that you call it. In this step, we are not expected to present the derivation or derive the solution from scratch. That is what I wish you would do, is to write down the equation and say this is of the form of a Bessel's equation or a Euler-Cauchy equation or a Legendre's equation, and directly write the next step as the general solution for that ODE.
So we can have that in our.
You should have it. If I were you, I would have it. Okay, because unless you actually have everything in your memory, which could happen if you end up practicing 300 problems between now and Monday. So this is the other key step. Okay, so if you spend a lot of time deriving it because you couldn't remember, that's when you become non-competitive in this exam. Okay. All right, so you got a solution for one of the functions. Third step is to use remaining boundary or initial conditions to set up the integrals for the generalized Fourier coefficients. This is the other key step. If you get to this step and express the correct integral, you have actually solved the problem, because the last step of actually getting the numbers out is a matter of time. If you make mistakes, eventually you will figure it out, right? So this step right here, I would say roughly, don't hold me on this. I would say this is about 25% of the credit. This is about 25%, and this is maybe, let's say, 30% or 35%. You get up to here, what remains is doing the integration. This is where I've had students call me to their desk at the exam and say, this is missing, that is not there, I can't do this, how should I do this, what about this? So evaluating integrals. So I will try to provide integral formulas or identities. It may turn out that I didn't give you enough information. In that case, I want to see how you exercise your best judgment to make calculations and provide and state suitable justifications. If you think the problem itself is strong, I made some mistake, something is missing, don't call me, write it on your sheet and we'll deal with it after the fact. If you really think you are finding out something that wasn't thought of, write it down. Okay. So this is what I'm expecting to see. This is about 15 to 20%. For each problem, same rubric. So to restate that, problem 1, 2D Cartesian Laplace. Problem 2, spherical polar Laplace. Problem 3, cylindrical radial wave equation. So this is uxx plus uyy equal to 0. This is the 1 over r squared partial r squared partial r plus 1 over r squared sine squared phi partial u over partial p squared equal to 0. And this is second, or I'll write it udt equal to c squared urr plus 1 over r ur. P2 and P3 could be interior or exterior, definitely no annular region. And P1 can be a rectangle or a square. Hopefully recording is on. Yeah. Any questions before we do some examples? We have about 15-20 minutes. Okay. So Let's try problem 2. That is the one that is appearing second, which I think is a cylindrical wave equation that is one of the expected questions. This solution process is entirely given in section 12.10. Whatever I'm about to say is already in section 12.10. Only thing I've changed is boundary conditions. Actually, I think I put annular just to make the practice a little bit interesting. So UTT equal to URR plus 1 over R UR. Obviously, I've set C squared equal to 1. I have a domain which I say runs from R equal to 1 to R equal to 2. And at R1, I say this is 0. And at R2, sorry, U is 0 and U is 0. The way I've stated this, you could still make the case that the Bessel function of second kind should not be there. Why? Because U equal to 0, right? Maybe not. Maybe we'll see. We'll see if there is a way that it can work. Okay, so where do you start? Start with the equation U of R comma T is H of R, making sure if I use the same notation, W of R and G of T. W of R and G of T. This is in section 12.10. So if you apply the separation of variables, what I wish to see is this. I have G double dot times W equal to W double prime plus 1 over R W prime. Just because I said I'm not expecting you to derive it, doesn't mean that you get to see this and just directly jump to the solution that you wish to use. You still have to bring it to a form that exactly matches with a template equation, and then with justification say, okay, this is Bessel's equation with new parameter such and such, and move forward. Okay. So we would have W double prime plus 1 over R W prime 1 over W. This also should multiply by G equals minus G double dot divided by G, and we'll say this is equal to, it's not minus K. Okay, so you will have W double prime plus 1 over R W prime plus K W equal to 0. Before you call like this is Bessel's equation, you might want to look up your sheet or write down the Bessel's equation to make sure you're not tricking yourself. Okay, what is the Bessel's equation? That is x squared y double prime plus xy prime plus x squared minus mu squared times y equal to 0. So if I rewrite this, this is y double prime plus y prime over x plus 1 minus mu squared over x squared times y equal to 0. This is not quite that. Not there yet. So for that, the book introduces a very simple transformation, S equal to KR. And you don't have to show me the steps. You can say using the transformation S equal to KR, we have d squared W over ds squared plus 1 over s dw over ds plus 1 over s squared times w or equal to 0, or you can write s squared d squared w ds squared plus s dw ds plus w equal to 0. This equation, once you see this or show this, you can say is Bessel's equation with new parameter being 0. I need to see this state so that I know I understand that you understood. Okay, so this is W. W. The equation in W. Equation of W of S. The solution for this would be W of S equal to, what will you write here? C1 of J nu 0 J0 of S plus C2 of Y0 of S. Of course, in the exam, whether it's the exterior or interior of a circle, you can choose C2 equal to 0, and what would be the reasoning for that?
You know where it's the infinite center for x equals 0.
You can say you want the solution to be analytic at either r equal to 0 or r equal to infinity. So I'll write here for circle or the semi-infinite region, that is the exterior, for choose C2 equal to 0 for ensuring u of r comma t is analytic. Analytic at either r equal to 0 or infinity. In this problem, what do we have? We have an annular region. We have an annular region. So although this won't appear on the exam, you can write W of k times 1 equal to C1 J naught of k plus C2 Y naught of k, and W of 2k equal to C1 J naught of 2k plus C2 Y naught of 2k. This is what you would do if you had a computer and a lot of time. Because to figure out what C1 and C2 are, you have to actually apply these boundary conditions, which let's see if anything simplifies. These two are given to be 0. We get something out of this. Maybe not. I don't want to get into this because I haven't fully thought it through. But let's say if you have a circular domain, like in the exam, U is analytic, and here we say U is 0 because it's a wave equation. You are holding one end fixed. Okay, you would make this argument to make C2 go away. So just get up to here and then jump to this step. Okay. So you get one function. How do we solve for k? So we have done this. Obtain the two ODEs. Get a general form of the solution for one of the ODEs, that is the Bessel function at k naught of s. We have done that. Now use the remaining kind of boundary conditions to get the values of the arbitrary constants, as well as we need to figure out what k is. K is still not. So we can say J naught of S equals K times 1 equal to 0. That's given in the boundary condition. So J naught of K equal to 0, which implies K takes values that are, or actually I should say, K takes values which are roots of J naught of X equal to 0. Either I will provide the list of roots, but it's just a theoretical point. You can say that from there on, J naught of alpha m, that is, you can say K takes values which are alpha m, where alpha m are the roots of the Bessel function. So the solution then becomes W of R is J naught of Km R, and since this depends on M, I'll add a M subscript to the W as well. Okay, so that we are going through step 3, then we need to use step 4. Step 4 is, I erased it, so I'll rewrite it, UTT equal to URR plus 1 over R UR. You have your domain R equal to 0, R equal to 1. At this point, U is given to be 0. So to figure out the solution for the other equation, you will write G double dot plus alpha m squared. K or K squared? K squared. Alpha m squared times G equal to 0. So this would be G of t equals A cos alpha mt plus B sin alpha mt. To get AM, use U of R comma t equal to 0 of f of R. That is the initial displacement, and to get Bm, use U of ut of R comma t equal to 0, which is G of R, let's say, which is the initial speed. In this problem, that is the mock problem I gave f of R to be 0, so that you can just say AM is 0. And the G of R is given as 1 minus R times R minus 2. So you'll have to do some integration, which unfortunately will also involve Bessel functions, for which I'll provide identity so that you could simplify it. Or I might say, if you have J naught of R, I'll give you a polynomial approximation for J naught so that the integration will be simpler. Okay. Again, my intention is to keep the stakes on it fairly low. I would even go far ahead and say, let's keep this 10 to 15% while I grade it, so that you don't get penalized too much for missing any integration. The problem 3 is the only thing we didn't do in problem 3 when we did the derivation last lecture is evaluate the Fourier coefficients. So I'm just hoping you would be able to do that because you're out of time. So for problem 3, you go to page page 596, equation 19. Page 596, equation 19. It is an equation for the Fourier coefficients an equal to 2n plus 1 divided by r power n. In our case, r is 1, 0 to pi, f of p, pn of cos p, sin phi dp. And what I have given as f of p is cos phi. Well, this to be cos phi. So obviously this is a polynomial. So a lot of places in this exam, you might be using the identity x power n sin omega x. But my intention while preparing the actual exam is to keep getting very simple integrals by invoking rather special functions that will make the integration go away or make it very simple. Okay, that's my intention. Okay. Before we go, any questions? Yeah.
Early on, it said that we should be able to manipulate Bessel's function. Are you saying just like take derivatives of it? And like what way do you?
No, I'm not a big mathematician in the sense I can't look at Bessel functions and do identities unless you give me an identity and give me several hours to do it. What I would do in this sort of a situation is write down the first 3 or 4 terms and settle for an approximate representation of the Bessel functions, which has 1 x squared, x to the 4th, x to the 6th, and so on, and use that in my integration and do it as quickly as I can. That's what I would do.
Gotcha.
But if you can actually do the integration with either Legendre polynomials or Bessel functions without having to compromise, that's actually a pretty good thing. I would be very happy to see it. So if you have any questions, please feel free to shoot me an email. Tomorrow I have I have classes and I have meetings in the afternoon, but on Friday I can definitely respond to emails, and Monday afternoon I'll be in my office. So if you want to swing by, Monday from 1 to 4, I'll be in my office. Yeah.
Have you think of any date about our final midterm exam?
It will be in the whatever the slot for this course. Like every course will have a reserved time. It will be during that time. You can go to the registrar's page and see that time. I don't want to misquote it, but I can look it up. You can also look it up. Sorry?
Maybe December 4th.
December 5th, it cannot be 4th because the last day of class is December 5th. So December 5th is Wednesday. So it can't be 4th. It has to be either 7th or later. 7th, like 6th is study day. It has to be 7th or later.